This is lesson 6, geometric growth and decay nth rule. The learning goal for this one is to see how an nth rule can be applied to geometric growth and decay, and to see how the rule can help us determine future values of compound interest or monetary decay. The success criteria for this one is to be able to create a geometric growth or decay nth rule for real life situations and use this to solve specific term values. So geometric models are similar to linear models in that you can also find a rule for the nth term. Or in other words, you don't have to rely on the previous term to get the next term. All you'll need is the common ratio and the initial value. So let's have a look at how this rule works and what you need to do to get a specific term within a sequence. For let's try that again. For growth, the rule to find the nth term is given by, to get any term of v of n, so remember that n just depends on what year or how many iterations, get your common ratio and put it to the power of whatever that term is. So in this case, if you want to look for v of 1, it's just a common ratio to the power of 1. To get the next one, maybe, or even v of 6, it's the common ratio to the power of 6. So just be careful here. This right here is a power. The n is a power. Then when you get the power of whatever the common ratio is, you just multiply it by v of 0, which is the initial amount. You got to remember that if you want to get the common ratio and all that's been given to you is a percentage rate, you just use that same formula again for growth and plug it into here, where this here is your rate and this here is the amount of compounds per year. The decay rule is exactly the same, where your R rate, your R value, common ratio, if it's decay, if you're given the rate, you just use minus. And you just have to be very careful. It looks exactly the same, but this R value must vary between 0 to 1 if it's a decay. So your R, your capital R, needs to be between 0 and 1. So look at this example here. The following recurrence relation can be used to model a compound interest investment, where the initial amount v of 0 is $500, and to get the next term v of n plus 1, it's equal to 1.0125 of v of n. Now this question is a little bit tricky because what it's asking for and what formulas you have to use, it's not too easy to place the two, and you'll see this in a second. Firstly, what is a common ratio? Now this one we know. The common ratio is very easy to find because it's always the R value that's in front of the v of n. So in this case, 1.0125 is your common ratio. For B, assuming interest is compounded monthly, and there are 12 months in a year, so 12 months, what is the yearly interest rate? Okay, firstly, we know we're finding a percentage. We're finding a percentage. Now we know what the percentage, we know what the common ratio is, we know what the capital R is, but what we don't know is what the small r, what the rate is. So let's plug in everything we know into the formula, not for this one, sorry, for this one here, because it's a compound interest investment. So we're adding R equals 1 plus small r over P all over 100. All right, our common ratio, we actually know what this is. This is 1.0125. Now this is going to be equal to 1 plus the rate is what we're trying to figure out. And the amount of compounds per year, P, because it's happening monthly, there are 12 months per year, our p-value is 12. And this is all over 100. So when you're in this situation, you can either solve this algebraically using your algebraic rules, or you can use your class-bed calculator using the solve function. That's what I'm going to do in this situation here. Okay, so I've just gone into the main calculation screen, made sure my keyboard is on. I want to use the solve function. So in math 1, to the right, third one down, we have the solve. And I'm literally just going to write everything in here. 1.0125 is equal to 1 plus. Now be very careful how you put this fraction part in. You're going to put fraction, and then that top part is a fraction again. So you're going to put a fraction on top of another fraction. Now in this case here, we're not going to use the letter R, we'll just use the letter X because X is on your keyboard. We're going to put 12 is the amount of compounds, and we're going to put 100 over 100. Now before we do this, just put the comma in and tell the calculator from this we're solving X. This is what we're looking for. Close the bracket, and your X value is going to be 15. So this means our rate for B, our rate is 15%. So interest is compounded monthly. What is the yearly interest rate? So what they will say is, here's your yearly interest rate. It's 15% per annum, compounded monthly. So they've just taken that 15%, split it into 12, and whatever they get, you add that to 1 because it's a common ratio. That's where the 0.125 comes from. For C, it's the same thing again. We're using the same formula, but assuming interest is compounded quarterly, what is the interest rate? So quarterly, for quarters, it's 4. There's 4 quarters. So we're going to do the exact same formula. We're going to do solve. We'll make it 1.0125 is equal to 1 plus fraction. Your rate is what you're trying to figure out, X. The amount of compounds per year in this case is 4, and this will be all over 100 to the side, comma, X. In this case, it's 5. So for quarterly, this one is 5%. Let's be consistent. Yeah, edit. Undo brush tool. Ah, doesn't want to do it. I don't know what's going on. Let's just erase you. That's easier. Here we go. All right, take 2. R is equal to 5%. Assuming interest is compounded fortnightly, what is the yearly interest rate? How many fortnights are there in a year? 26 fortnights. Same formula. What did I do wrong? Ah, I know what I did wrong. I forgot to add the 1 plus. Silly Mr. Herman. He's good. I could edit this out. You know what? I'm going to keep this in so you can see that even the best mathematicians make mistakes. I'm not the best mathematician. I don't know what I'm on about. There we go. X over 26 or over 100, comma, X. Much better, 32.5% per annum. There we go. So this one is a bit of a tricky one because it's not obvious that you have to use a solve function, because usually we're assuming that we're looking for big R, but in this case we're looking for small r given what big R is. Or finding the rate given what the common ratio is. Two more examples. A recurrence relation can be used to model the reducing balance depreciation of a car purchased at $18,500, where the value of the car depreciates at a rate of 10% per year. For A, we are going to write a recurrence relation to model this situation. This is simple. And this is actually calling back to the previous one. First, we need to find out what R is, capital R. And because this is decay, it depreciates, it's 1 minus R over P all over 100. We know that this is just per year, so our capital R common ratio is 1 minus 10 over 100, and this is equal to 0.9. So using this recurrence relation, always start off with V0 is equal to the initial amount. Much better. To get the next term, V of n plus 1, get your previous term, V of n. What is going on? I'm making all these mistakes. 0.9 times V of n. There's our recurrence relation. This is between 0 and 1, so it's going to decrease over time. Now, we need to write the rule to calculate the nth term in this situation. So whenever you write a rule, you always start off with what V of n is going to be equal to. So you're not going to start with V of 0, we're just jumping straight into a generalized term. So V of n is going to be equal to what the common ratio is, R to the power of n times the V of 0. So this is the general format, but there are a few values we do know. Our common ratio is 0.9. This is to the power of n. And our initial is 18,500. And this right here is our rule. Right here, we have our rule following that template. And the difference, and I'm going to keep saying this, the difference between recurrence relation and a rule, this recurrence relation tells you how to get the next term using the previous term, where the rule tells you any term that you want, provided that you know what the common ratio is and you know what the initial amount is. And that's where that n to the power comes from. Last example here. The following recurrence relation can be used to model a compound interest investment per annum. V of 0 is equal to 1,000. And to get the next term, you take the previous term and multiply by 1.08. First question, how much was invested at the start? Very simple. Investment at the start, $1,000. What is the interest rate? Very simple. The interest rate, we know what the common ratio is. So to get our interest rate, remember I always go 1.08 minus 1 and times this by 100. So our interest rate in this case is 8% per annum. And this is small r. C. Write the rule to calculate the nth term for the situation. So remember, the template rule is V of n is equal to R of n times V of 0. We're going to find what our R is, we've got to find what our initial amount is, V of 0, and we can plug this in. V of n is equal to our common ratio, which is already being provided to us within the question, 1.08, to the power of n times whatever the initial amount is, 1,000. There's our rule, and now we're going to use our rule to help us solve for D. What is the future value of an investment after 20 years? So after 20 years, all we're doing is just finding V of 20. And we're going to replace 1.08, we're going to replace the n with a 20, so that, remember, that's to the power of 20. So let's put this into a calculator, class my calculator to make sure that we're doing this correctly. We'll go ahead and clear this all first. Okay, so 1.08. Now remember, to the power of, when you get your keyboard out, your power button is in Math 1 by pressing this button here. Power to 20. Make sure that when you do the next part, you go across first, and then you do times 1,000. So after 20 years, the investment for compound interest is $4,660.96. Because that's a 7, that 5 gets bumped up to 1. So V of 20 is equal to 4660.96. Last question, E. How many years will it take for the investment to reach $6,000? Now there are two ways you can use the calculator, but the only problem is it's not necessarily a problem. We want to be focusing on the actual rule itself. So I can plug this recurrence relation in and then see when it will hit past $6,000. The other way is to just write down what we do know. So $6,000 is equal to 1.08. So I'm just writing this rule with the red box around, this rule in there. But our value we already know, because that's what we're trying to, that's what's been given to us, 6,000. It's the n value, when it reaches n, is what we're trying to solve. So you would go ahead and just use a calculator and use a solve function, type in everything you do know. Instead of using the letter n, we're just going to use x, so put the power and then press x within your keyboard. Make sure you go across. We're going to times this by 1000, comma x, because that's what we're solving for. Close the bracket. And this will come up with 23.28138293. Rule of thumb is if it just goes a little bit past that decimal point, you just round it up straight to 24. So in this case here, n is equal to 23.281. 1 ... Therefore, it will take 24 years. That's all there is to it for geometric growth and decay nth rule. Check your worksheet, see what questions you need to do, and I'll catch you in the next video. See you later, bye bye.